All right, by my reckoning, we have just ticked up the hour on the hour, and I will offer what I now call the Zoom minute to allow people to deal with involuntary upgrades to Zoom that it sometimes requires, and which means I will be starting to introduce our speaker at it's 3 over there, 3:01 Central Time. I should have special music, on hold music for the Zoom minute, the Zoom upgrade minute.
Like the interlude in Monty Python and the Holy Grail.
Yeah, or like the Jeopardy music.
Okay.
Well, that's about half as long as it used to be. Yeah, that sort of thing.
Yes.
All right. Oh, yes, I have 1 minute after the hour. Okay, so it is our distinct honor and pleasure and all that to have Dr. Oliver White here to give us a talk about Pluto. I will read some biographical information. Dr. White is a research scientist at the SETI Institute, although he is resident at the NASA Ames Research Center. Since getting his PhD in planetary science at University College London in 2010, his research has focused on a range of topics related to the topographic characterization and geologic evolution of planetary landscapes, primarily in the outer solar system. During his postdoctoral position at the Lunar Planetary Institute, I've heard of that, from 2010 to 2013, he worked with Paul Schenk to produce stereo and shape from shading digital elevation models of Io and the Saturnian and mid-sized icy satellites. As a NASA postdoctoral program fellow at NASA Ames from 2014 to 2017, he used landform evolution modeling to investigate the formation and evolution of Callisto's ice pinnacle terrain. He is a co-I on the geological and geophysical investigation team of the New Horizons mission. And in June 2022, he completed a first draft of a global geologic map of Pluto that will be published by the USGS, which I believe is going to talk about. And let me just add one more thing. Ollie is my co-investigator on my NFDAP grant to study Pluto, the tectonics. And it has been just wonderful working with him. He always gets, whenever I desperately need something done, because I've been doing some other stuff, he comes up with the complementary material right away. So it's been great working with him. So I'll on that note, I'll just hand it over. Go to Oliver White. Thank you.
Well, thank you very much, Wingman Pat, for that. And thank you very much for inviting me to give this seminar. It's already making beeping sounds at me. There we go. So yes, so yeah, that's right. The subject of my seminar is Pluto, which has undergone quite a character arc since it was discovered by Clyde Tombaugh back in 1930 and declared the 9th planet. Over the rest of the 20th century, more discoveries about it were kind of few and far between, given how small and far away it was. And after the Voyagers wrapped up their missions in the late 80s, it sort of got reputation as the astronomer's planet, as emphasized by this stamp at the bottom left there. And really until New Horizons, the only decent imaging we had came from Hubble, which sort of provided some murky view of the surface, nothing specific. And eventually, after various attempts to try and get a mission to the Kuiper Belt, New Horizons succeeded and was launched in January 2006, and just a few months later, the IAU downgraded it to a dwarf planet, or a bit reclassified, more diplomatic, as a dwarf planet. But such matters were sort of at the back of our minds when New Horizons finally flew by Pluto in July of 2015, and gave all of us on the team plenty to salivate over, as you can see in this picture on the right here of the first reveal on July the 15th. So just to provide a bit of context for Pluto, since not everyone breathes Pluto like I seem to have done the last several years. Pluto has an orbital period of 248 Earth years, quite a high orbital eccentricity and inclination that takes it about 30 AU close to the sun, and farthest away 49 AU. So its orbit covers pretty much the entire width of the Kuiper Belt. It gives its name to the Plutino class of Kuiper Belt objects, which orbit in a 3-2 resonance with a Neptune. And most importantly, for its in terms of governing its climate and therefore its surface geology, it has a very high obliquity that ranges between 103 and 127 degrees over a 2.5 million year cycle. Prior to New Horizons, the amount that we sort of knew confidently about Pluto sort of practically fit on the back of a postcard. We reckon it had a diameter of 2390 kilometers, which has been refined after New Horizons, 2377 kilometers. If you were to unfold Pluto's area, it would cover most of North America, as you can see on the left there. I've mentioned that, yes, Hubble gave us our best imaging, and so showed there was sort of strong contrast in albedo and color across its surface, but no actual geological features could be discerned. We did detect volatile ices on its surface, nitrogen and methane, and it was also found that Pluto had a thin nitrogen atmosphere confirmed by stellar occultations, which is something of a surprise for such a small object. And some modeling studies as well in the 90s and 2000s reckon that Pluto is most likely differentiated into a rocky core, a water ocean, and a water ice crust. And some New Horizons observations have since then confirmed that there is a subsurface ocean. So regardless of what we all sort of thought we might see at Pluto prior to the flyby, the first images we got that pretty much blew all expectations out of the water, and we were at once busy analyzing this fantastic world, which surprised us because of the great range of morphologies we saw across its surface, but also the great range of impact crater densities that these landscapes show. There's evidently a very wide range of surface ages across Pluto, and I actually started mapping some structures on Pluto just a few days after the flyby. So this map has kind of been more than 7 years in the making, and it was something I wanted to do quite early on, is try and get funding to make a USGS map to sort of tell a cartographic story of Pluto's geological history, which eventually stuck with a PDART, and so the results of that I will show you today. But while we did get a great first close-up look of Pluto, we only got a view of just a portion of it. We only, since this was a flyby mission, we only got good resolution of the near side of Pluto, which I'm defining as the part of Pluto that was seen with imaging of 1 kilometer per pixel or better. The far side has imaging ranging from about 2 to 40 kilometers per pixel, a very enormous range of resolutions there. And so this is obviously a pertinent issue when geologically mapping Pluto that I'll get onto in a few slides. And there are also other imaging parameters that also differed quite broadly across the surface, the incidence angle and emission angle, all of which you had to keep in mind when mapping. But in addition, Pluto, was, as I mentioned, has a high obliquity. Its current obliquity is 119 degrees. And at the moment, the northern hemisphere is entering summer and the southern hemisphere winter. So the southern latitudes were all in darkness. We couldn't see any of those, with the exception of this strip of haze-lit zone here, because Pluto has a thin atmosphere. We got some bonus mapping in the form of this strip of terrain here that was dimly lit by Pluto's haze in its atmosphere. So we got a little more than we anticipated. Some other data products that have been extremely useful for producing a geologic map is topography. This stereotopographic map of the near side was made by a certain Paul Schenk that's been quite indispensable. We don't have any of this for the far side, and the resolution's too low, but we do have some occasional limb profiles across the far side that have certainly been very useful in defining some of the units there. And we also have some spectral data of some of the various materials, including some exotic ices like methane and nitrogen across the surface that have been handy. So to cut to the chase, this is the version of the geologic map that was submitted for review back in June. I've actually got those reviews back now, so the final product will look a bit different to this. But in this version, we have 45 units mapped globally, and I've actually mapped ones on the far side separately because the resolution and data quality is so different there. I figured it worked out with the USGS that we should probably map them separately, even though quite a few of these units I think have direct analogues on the other side. We're just being prudent and mapping them separately here. So in terms of determining the ages of these different landscapes, we use sort of standard USGS geological mapping techniques of cross-cutting relations and also crater statistics to construct a stratigraphy of mapped units. And ideally, each of these map units has a distinct genesis and modification history. At the bottom left is a map of craters mapped across Pluto by my Minister for Cratering, Kelsey Singer, from a paper she produced in 2019. In solar system terms, Pluto is somewhat moderately cratered, I would say, but with great range of crater densities across the surface. And Kelsey found that only really craters in a sort of single diameter bin of 7 to 25 kilometers, there are enough in that bin to produce meaningful spatial density analysis, with 7 kilometers being the minimum feature size we map of any kind. On Pluto, she reckoned those above 25 were too few to yield meaningful statistics. So in this R plot here, which plots sort of crater density, sort of as represented by this R value here, where higher R values are sort of a higher crater spatial density, plots that against crater diameter. That's why we have just a single bin here centered on the geometric mean of 7 and 25 kilometers, with all of the units clustered there. And these are model ages here provided by Greenstreet and Owl in her Kuiper Belt crater modeling, crater size distribution modeling study from 2015. This is a bit of a more easy on the eyes version of the R plot over here that stretches this out, expands it, so you can sort of just plotting the R values against a unit. And I'll invoke this a bit in some of the later slides. So using stratigraphy, so yes, we use cross-cutting and crater ages to define the correlation of map units here. So it just shows the stratigraphy of all mapped units. And we reckon that there are 6 distinct geological periods on Pluto, each of which is sort of defined by a particular episode of geologic activity, which for the most part is dunking a big load of deposits of some kind or another at some location on the surface, which is something that seems to have happened at sort of quite regular episodes throughout Pluto's history. And so I will in a moment sort of take you on a tour of these various episodes. But first, I also want to impress upon you the importance of climate when considering the genesis of these various terrains. So as I mentioned, Pluto has an extreme obliquity that also varies a lot. And so this graph on the left here shows how the insolation across Pluto differs with latitude for different obliquities. And you can see in general, the insolation tends to be highest at the poles and lowest in the equatorial region across an obliquity cycle. And this figure on the right here is from a paper by Rick Binzel from 2017, focusing on Pluto's climate zones. You can see there's the Arctic up here, which is where you get the most extreme seasons. You get sort of several decades of well, more than a century of summer, followed by more than a century of winter at each pole. And these arrows show the oscillation zones for each of the climate zones. The equatorial region, you get the diurnal zone here, which is a much more mild climate there, much less temperature and seasonal extremes there. And the bottom one shows the tropics. So you have an interesting situation on Pluto where you have the so-called tropical Arctic, because there's a zone between 37 degrees and 53 degrees where you get the tropics and the Arctic overlapping, which is where we think you would get sort of most active mobilization of volatiles on sort of in a sub-seasonal time scale. So across a whole Plutonian year, that's where you get the most volatile, most mobilization of volatiles. So to start with the Sputnikian period, this is the youngest period on Pluto, and it consists entirely of thick deposits of Pluto's nitrogen ice on the surface, most of which resides in Sputnik Planitia, here, the left-hand side of Pluto's famous heart that dominates its encounter hemisphere. And but there are smaller deposits that are scattered on the floors of depressions and craters that extend to the east, and we haven't managed to spot any impact craters at all on any of these units, as far down as 76 meters per pixel. So really, all of these terrains can only be a maximum of about 50 million years old. Now, in the case of Sputnik Planitia, we recognize that its deposits fill this enormous elliptical depression that we reckon is an ancient impact basin. So I show in red here the outline of Sputnik Planitia, and in blue is the approximate topographic crest of the Sputnik Basin, which is apparently absent at its southern end, so Sputnik can sort of spill over to terrain at the south. And here in the geologic map here, so the Sputnikian stuff is mapped in these yellow units. And in the center and north of Sputnik Planitia, we saw early on that the plains are divided into these ovoid cells by these this network of these troughs and with these central ridges here. And given what we know about nitrogen ice, sort of very low viscosity and easily mobilized, we reckon that Sputnik Planitia is actively convecting here. Just the minimal heat flow that trickles out of Pluto causes the nitrogen ice to convect. So yeah, produces these surface horizontal velocities of just a few centimeters a year. So it's this convecting zone here is probably old no more than about 500,000 years. And so, yes, and Bill McKinnon's study, which sort of studied convection that I was involved on, reckoned that sort of the average cell diameter of these cells means that the thickness of the Sputnik Planitia is about 3 to 6 kilometers, which I've used this value in the cross section that I've done across the near side, a portion of it covering Sputnik Planitia. You can see here. And we have noticed, however, that these cells often become larger and kind of interconnected towards the central portion of Sputnik Planitia. The cellular pattern kind of breaks up quite a bit here. So we think that the Sputnik Basin is actually deeper here, and the deposits are kind of thicker, so much so that it kind of disrupts the convective process, which I've tried to emphasize here with some of these dotted lines showing some of the breakup of the convective process there. As for the southern end of Sputnik Planitia, we don't see sort of the ridge and trough pattern here. Rather, we see a lot of pitting in the plains here, which we also see in the convective terrain. But the pits here tend to reach rather larger sizes, and they tend to organize themselves into these rather amazing sort of wave-like fields, sort of with these chains of aligned pits here. So we think the pits are due to sublimation of the nitrogen ice into the atmosphere, and that these sort of wave-like patterns are perhaps due to stress anisotropies extending throughout the ice, probably most likely due to the ice flowing, kind of stretches out these pits into these crazy patterns you see here. Also, this unit of mapped in sort of this more beigey color on the right here indicates these sort of little accumulations of low hills that we see clustering in the eastern edge of Sputnik Planitia. And we also see here sort of nitrogen ice that's coated East Tombau Regio in highlands to the east of Sputnik Planitia. Is actually flowing back into Sputnik Planitia through these valley glaciers. We think these are moraine trails of blocks, sort of forming these lateral moraine trails with the valley glaciers here. And that these glaciers are actually eroding sort of blocks of methane ice from the highlands here that are then carried out into Sputnik Planitia, because methane ice is slightly less dense than nitrogen ice, and clustering to form these clusters of hills when they become subject to the convective regime in the center of Sputnik Planitia there. So we now travel from Sputnik to the youngest highlands terrain on Pluto, which I've called the Rhaetian unit, named after Wright Mons, which along with Picard Mons, a couple of enormous mountains to the south of Sputnik Planitia that are unique on Pluto because they show these enormous central depressions. You can see quite well in the topography on the right here. This was kind of tricky to map here because this group is mostly covered by the hazelit imaging, so textures aren't quite so apparent in the low signal to noise you get in this haze imaging here. But we also can tell that this is very lightly cratered terrain, only a few sub-kilometer impacts, sort of not even big enough to include on a 1 to 7 million scale map. So Kelsey reckons that this terrain probably dates to Pluto's later Middle Age, less than 2 billion years. Now, what this terrain is kind of an enigma and may well remain that way until we eventually go back to Pluto. Who knows when that'll be? But based on the fact that these look like mountains with holes in the top, our initial hypothesis was that there may be cryovolcanic in some way. Although if so, then they're very different to sort of large sort of shield volcanoes that we get in the inner solar system. This cross-section here compares Mauna Loa, currently in a bit of a temper itself in Hawaii, with Wright Mons. The scale of these central depressions are massive compared to the mountain itself, so much so that they're almost like depressions surrounded by mountains than mountains with giant depressions. But as for the sort of surface texture of them, they show this interesting hummocky texture at a 10-kilometer scale here, and at a lower scale, we also see this blocky texture superimposed on the hummocks. And we also see sort of scattered about these carvi, these rimless depressions here, and also some features that sort of look a bit like domes, like Coleman Mons here. And so generally, the cryovolcanic hypothesis has persisted, although exactly how the cryovolcanism would proceed is still not been sort of worked out sort of satisfactorily enough. We sort of don't really see any obvious flow fronts or source vents that the flows are linked to, and given that we see very sort of steep slopes here, particularly in the central depressions, there must be a decent contribution of water ice to the composition of these things. And since water ice is so refractory, it requires quite a bit of energy, or at least a lot of mixing with some impurities to lower the sort of melting point of the sort of cryo melts to sort of actually erupt. And so Kelsey's paper from 2021 that I was involved in reckons that these sort of mountains may not actually be the sort of volcanic centers at all, but rather sort of you get eruption of multiple domes that sort of merge to form these sort of complex large-scale structures in this region. And also Jeff, my sort of co-worker at Ames, has sort of offered an alternative hypothesis whereby actually you might get gaseous eruptions that sort of where the gas settles out and recondenses across the landscape to produce what is sort of like an accretion texture with these domes here. So yes, it's still quite enigmatic, and really for the purpose of my map, I do invoke the cryovolcanic hypothesis, but the basic interpretation is that it is a very young deposit that has emplaced itself in just the last 2 billion years on Pluto, and that's sort of the most we can say with any real degree of confidence. So moving to the east of Sputnik, we encounter the Tartarin group of units, which consist of these methane-rich, quite elevated terrain that stretches very far from the east of Sputnik Planitia within its equatorial region. And you'll notice that most of these units tend to occur in the far side of Pluto. And the most characteristic of these units is the bladed terrain, which this map at the bottom left is indicated in the DEM of the near side by this white sort of very elevated terrain here, and this is where the far side limb profiles really come into play. Do we think this intermediate albedo terrain that extends along the equator, this shows up as being very elevated with respect to terrain on either side of it in the limb profiles. So we have gone ahead and mapped this green stuff and sort of this forest green here as a continuation of the bladed terrain deposits across most of the far side and even peeking into the near side back again here. And this is also helped along by this far side methane map, which shows sort of high methane abundance of these areas as well. So having a closer look at these landscapes in the near side, this is the bladed terrain sort of in the top center image here. You can quite clearly see how it gets its name. It sort of forms these big bulbous swells with this texture of these north-northeast, south-southwest aligned ridges that tend to be a few kilometers apart, but can reach several hundreds of meters high. And we also identified this other sort of methane-rich terrain called arcuate terrain, which you can see extending north of the bladed terrain here, and which is also superposed by the bladed terrain, but which sort of has this arcuate texture that's sort of more east-west aligned. So we reckon that these deposits here of methane ice, as a result of these separate episodes of this deposition of methane ice in Pluto's equator, probably in Pluto's middle age, because we see a few large craters in the deposits here, but generally still pretty lightly cratered in general across it, and certainly very few small craters can be identified. And then sort of once deposition of this stuff had happened, then the climate apparently sort of transitioned to one that is more preferable for sublimation. So and that is what gave this sort of bladed texture of the bladed terrain deposits as the methane ice sublimated away. Sort of in between the bladed terrain and sponnic glacier, we get what I've called the bright mantled pitted terrain, the boundary of which is quite hard to determine between that and the bladed terrain, mostly in a sort of high sun angles. It's easiest to determine because this is all much higher albedo than the bladed terrain. And I think that this is also bladed terrain, but at somewhat slightly lower elevations, and where it's being, you get a lot of deposition of nitrogen ice here that is eroding the bladed terrain to sort of form this kind of more pitted sort of texture here. Yes, so yeah, and I think the same thing has probably happened for the arcuate terrain in this minty colored unit I've mapped at the top here. So yeah, evidently sort of some evidence for sort of a large portion of Pluto's methane ice being stored in these enormous deposits that are aligned along its equator. Moving to the northeast of Sputnik, we encountered the Hayabusan unit, mapped in sort of pink here. This is a more methane ice-rich material that mantles the Arctic terrain up here, although it appears quite different to the deposits of the Tartaran unit. We think that it reaches probably hundreds of meters thick here, and it's characterized sort of in its best preserved portions by what sort of very much looks like an accrescence, a smooth accrescence texture, whereby the landscape seems to have been coated by these deposits sort of equally at sort of low and high evolution, low and high elevation. So you don't just get deposits sort of concentrating at high elevation or sort of in basins. So yeah, this is what sort of a uniform accrescence texture here, whereby the methane has just coated the landscape equally. You also see a lot of pits in this landscape, as we do sort of east of Sputnik in general, that show these sort of lightly pitted floor deposits, like these ones here, and also these chains of these smaller pits that are often sort of aligned along structural trends in the region. We see quite a few sort of northwest southeast aligned fractures that these things are aligned with. So as we move sort of away from some of the more elevated parts of the Hayabusan formation to some more depressed portions, we find that it sort of has the same long wavelength texture, sort of these gently undulating landscape, but it also appears rather more rugged than terrain at higher elevation. And we see this sort of gets this sort of more pitted and sort of scabland-like texture here, which suggests that the methane mantle is being degraded quite a bit by sublimation erosion here. And everywhere the Hayabusan units are superposed by the Tartaran units, and we think that the Hayabusan mantle dates Pluto's early Middle Age. So this is the eastern portion of the cross section here. I've sort of indicated the Hayabusan mantle here being superposed by first the arcuate terrain and then the bladed terrain on top. So a lot of evidence for sort of mantling having coated much of Pluto's eastern hemisphere on its near side. So now we come to the oldest terrains on Pluto, which for the time being I'm lumping together, the Veneran and the Bernian. I'll sort of explain more sort of what I think the differences between these two periods a bit later on. So this is the most heavily cratered terrains, and so these tend to hog most of the R plot, as you can see on here, since there aren't many others besides these that have sort of significant craters. And there are, and sort of just as to re-invoke the correlation of map units, this is where we are down here with the Hayabusan, Tartaran, Rhaetian, and Sputnikian sort of getting increasingly younger up there. And there are 5 important elements to these ancient terrains. The ridge trough system, ancient glaciated terrains, the Sputnik Mountains, mantled terrains, and non-glaciated, non-mantled plains, which I'll now describe for you. And so, yeah, the first is this incredible landform, the ridge trough system, that took quite a while for us to identify. Paul Schenk managed to, after a few years in his topographic map, because it's kind of subtle in the actual imaging. It's basically this enormous tectonic band that extends from Pluto's North Pole to quite far into the southern hemisphere beyond the terminator, and it consists of these sort of this very eroded, cratered band of various tectonic features, these graben, troughs, ridges, tilted blocks, plateaus, and these elongate depressions. Some of the elongate depressions are shown in this dark terrain on the left here, where they're connected by these graben here. And it forms what seems to be a great circle around Pluto. And these things are kind of quite rare across the solar system. Perhaps the best analog is another similar system on Tethys, Ithaca Chasma, which extends 75% of the way around Tethys. We can trace this one on Pluto for about 40% of the way around its circumference. But I'll get back onto this in a few slides. We then get to the glaciated terrains. So these tend to concentrate to the north and southwest of Sputnik, and indeed much of the ridge trough system itself is does seem to have been affected by glacial dissection. So these landscapes do show these sort of quite eroded, dissected texture across them. You can see some of these some of these valleys that have eroded into these this mountain chain, Picafetta Montes here, and these they often sort of empty out into these broad plains that we think was covered by glacial nitrogneiss early in Pluto's history. There are also some some more actual dendritic valley networks we can see, particularly to the well-formed ones to the northeast of Sputnik Planitia. But these do seem to concentrate sort of at these longitudes around Sputnik Planitia. We don't really see any evidence sort of in the far east or the far west for glacial landscapes. And as for the Sputnik Mountains, which is some of the most dramatic landforms on Pluto, we think that tectonism and glaciation have combined to form these mountains. So as you can see here in the topography on the right, these form these sort of chaotic ranges of mountains that extend along the west edge of Sputnik Planitia. The mountains that form this jumbled blocks you can see in these imaging at the bottom here. They can rise very high above Sputnik Planitia, up to 5 kilometers with steep slopes of 30 degrees, and they are all made of water ice. Here, some of them seem to be isolated in these in the plains of Sputnik. They've sort of broken away from the pack, whereas the within the ranges themselves, we can see some sort of stretches, expanses of nitrogen ice that separate the mountains. And you can see at the top left here in the map, a lot of them seem to be occur where the ridge trough system actually crosses Sputnik Planitia here. It intersects the edge of it here. And we think that these mountains have formed due to the crust here, which has been brecciated not just by the Sputnik impact itself, but also tectonized by the ridge trough system. And that's allowed nitrogen ice, both glacial nitrogen ice from the uplands, but also nitrogen ice from Sputnik Planitia itself, to intrude into the crust here and break off this crust that is now sort of gathered together in this sort of giant log jam of crustal fragments that are clustered at the west of Sputnik Planitia to form these incredible mountain ranges here. And now we move to the far west of the near side, which has got rather less attention in the literature since the flyby, because it's overall it's amongst the flattest terrain of Pluto's uplands, and is generally rather less extrovert and flamboyant than the younger terrains to the east. But it does have an especially interesting story to tell, I think. The first type of terrain here are the mantled terrains, but the mantle here is kind of quite different to that to what we see in Hayabusa and Tartarus. So Paul's stereo DEM doesn't really pick up the thickness sort of scarps of the mantle here, and so it's probably less than the vertical precision of his DEM, so probably no more than a few hundred meters thick here. The mantle sort of forms this sort of kind of fretted and sometimes knobby terrain here, and it seems to be quite eroded. In fact, we think these exhumed plains here are probably lower portions of the mantle that have been exhumed through erosion of overlying mantle to the right here. And the knobby morphology, we think, gets its appearance from sublimation erosion of the mantling material. It doesn't really look glacial in its origin. And if you stretch the sort of imaging of New Horizons imaging in the dark region of Cthulhu Macula here, you can also see that this rough knobby texture extends into the south. So this mantle, as well as covering a lot of the northwestern Arctic latitudes, also seems to extend quite far to the south as well. And then you have the non-mantled plains, which are far to the west, particularly well expressed in Vega Terra here. So we don't think this terrain ever seems to have been mantled at all, and doesn't show any evidence for glacial dissection. Although some of these plains we think have been exhumed by erosion of overlying mantling material, sort of like this sort of grayish purplish stuff I'm indicating with the cursor here. Particularly kind of interesting unit of these plains is expressed by Lunacod Planitia here, which is interesting because it shows very few small craters, and it's also surrounded to the west and south by Piri Rupes, this big erosional scarp. So we're thinking maybe sort of a sublimation erosion of perhaps overlying mantle here has been especially fierce, especially strong, and sort of eliminated a lot of the small craters that once existed here. So the next couple of slides is stuff that probably isn't going to make it into the final map because it's maybe a bit too hypothesis testy, but it's something that I think is certainly very interesting in its own right, and something I will likely sort of pursue sort of in a separate study after the map is published. But these we can see that these ancient terrains of Pluto show a lot of evidence for tectonization, sort of glaciation and mantling, but is there any rhythm or rhyme to why we get these particular landscapes where we see them? And I think the answer may lie in Pluto's history of a true polar wander. So we know that true polar wander has occurred on Pluto which occurred in response to the appearance of the Sputnik impact basin and its loading with nitrogen ice, and also the uplifting of Pluto's subsurface ocean underneath it. There have been a few studies in the past, Nemo and Keen from 2016, who are modeled true polar wander in response to these effects. And so in the sage words of Paul Schenk from his cartography paper in 2018, if Pluto has undergone polar wander, then none of these terrains are in the original locations and should be considered in evaluating their origins. So true polar wander would have occurred early on. The impact basin, we think, formed very early on. It would have been filled, it would have acted as a very strong cold trap for nitrogen ice and would have been filled very quickly. And so true polar wander would have been an early phenomenon. So Paul actually suggested in his paper that the Great Circle, which is the ridge trough system, might actually have been oriented along a paleo equator prior to true polar wander. So I wondered if Pluto's ancient geology might actually reflect climate zone configuration before true polar wander in response to the Sputnik Planitia happened. And so I just had a go at basically taking the current climate zone boundaries that I showed you sort of in a slide earlier in the presentation. I stuck them on in their current configuration here. These are the lines in blue. And then I took the same climate zone boundaries and shifted them so that they're oriented with the ridge trough system, sort of as the paleo equator. These are these lines in sort of red and yellow and orange here. And I found some quite interesting results that cleared up some sort of nagging sort of thoughts in my mind that had been plaguing me as I was mapping these western longitudes here. So first, to focus on the glaciated units, which again marked in black here, we find that the before true polar wander, sort of with the climate zones sort of oriented along as sort of these hot colors here, these glaciated zones would have been confined to within 31 degrees of the paleo equator. In Pluto's current climate and current orientation, we also see that its glaciated terrains are sort of in the uplands are also located within Pluto's diurnal zone. So this diurnal zone is quite mild, and nitrogen ice is quite volatile. You would expect it to be most stable in the diurnal zone here, and so it sort of follows that in this pre-true polar wander orientation, it also would have been sort of stable in the paleo diurnal zone here. But after true polar wander, it would have then, Pluto would have been oriented such that these glacial landscapes would have occupied the whole range of latitudes from the equator all the way to the pole. And I think glaciation, since we see glaciation right at the edge of Sputnik Planitia, it probably persisted in these latitudes, particularly at low elevations for some time after that, but gradually as all of it migrated to Sputnik Planitia, it would have become sort of the ice would have receded by sublimation and redeposition from these locations and never sort of returned there. So we see evidence of the ancient glacial landscapes here, but after that, pretty much all of the nitrogen ice glaciation on Pluto would have been confined to Sputnik and to certain locations sort of along its current diurnal zone. Now, if we now consider the mantling units, back in before true polar wander, these would have occupied the paleo mid latitudes and the sort of paleo, particularly also the paleo tropical Arctic between the yellow and orange lines here. So the seasons would have been more sort of active sort of once we get away from the diurnal zone here, and we've seen more active volatile mobilization in these latitudes that promote this ongoing deposition and erosion of mantling material, and so indeed we actually do find that a lot of the mantling material seems to occur within these paleo mid latitudes. But once Pluto reoriented, then in this new configuration, sort of some of these mantles would have ended up again in the mid-latitudes, and there would have been some continuation of volatile mobilization, but some of them would have ended up in the diurnal zone here. And given that this terrain is quite flat, there was not really any sort of topographic sort of expression that would have sort of promoted additional sort of deposition of methane ice here, the way sort of it has done in the bladed terrain in the east, where sort of the elevated terrain here sort of creates a runaway effect, where you have sort of initial methane deposition that then increases in elevation, and then you get more and more. There wasn't really any of that here, and instead it's been covered by this sort of haze particle layers here, this dark stuff, which is what we think are tholins that are sort of covering, depositing out of the atmosphere and covering a lot of the equatorial regions, because in the diurnal zone here, in a quite mild climate, there's nothing to really disrupt the sort of layer of tholins here, and so that would have shut off any more mobilization for the mantle here. And indeed, this part of the mantle does seem to be the oldest of all the mantled terrains we see in the western part of the near side here. And then we finally get to the plains units here. So before reorientation, this would have occupied the polar zone. You can see the paleo pole here. And this zone would have had the most extreme seasons. So sort of like sort of 124 years of constant sunlight, followed by 124 years of constant darkness. So while the seasons would have been extreme here, because you basically get sort of a lot of volatiles that flock here in the winter, but then when it changes to summer, you get all those volatiles are sublimated away and leave to the opposite pole. So that means that the polar zone is not really sort of conducive to build up of thick sort of volatile ice deposits the way that the mid-latitudes are, where you get ongoing deposition and erosion happening all throughout a Plutonian year. So before true polar wander, this would have not been, you wouldn't really have got much buildup of deposits here. And then after true polar wander, it would have ended up in the sort of the diurnal zone with a mild climate, and like the mantling, it's very flat, and so there wouldn't have really been any much impetus here for further deposition of volatiles. So it has remained essentially just smooth plains with craters for its entire existence, this region here. And another interesting thing is that somehow, for some reason, in the diurnal zone, the present diurnal zone, there seems to be quite conducive to sublimation of volatiles here. We get Lunacod Planitia here, where I think especially strong sublimation has occurred, and also quite a lot of the mantle seems to have been eaten away here, producing this knobby terrain here. So again, so it's quite a lot to take in there, and quite a lot to think about in what Pat calls this climactic bingo chart here. But just a few thoughts. I've realized I haven't got much time left, but I'll just run quickly over this. So in this interpretation, the Bernian, I should point out, is named after this large impact basin here, the only multi-ranged impact basin on Pluto. I would say in this interpretation, the Bernian is basically the period sort of that best expressed by these plains here that sort of formed in the Bernian, the earliest period of Pluto, and haven't really been modified since. Well, the Veneran era is characterized by some ongoing volatile mobilization and glaciation happening after Sputnik Planitia has formed here. But then activity kind of ceases once all the glacial ice is retreated, and mobilization volatiles here ceases. This does sort of imply that Pluto's obliquid cycle has been quite constant since its earliest days. If it was very different, then these climate zones may even actually been inverted, and you would have had sort of high insolation at the equator and sort of low insolation at the poles. But based on this interpretation, this hypothesis, I don't really think that's happened. I think its obliquid cycle has stayed kind of the same. It also suggests that a lot of Pluto's near side pre-true polar wander geology was not completely wiped out by the Sputnik impact. And then another thing to consider is that if the trough system was the paleo equator, then the initial latitude of the basin was quite low at about 15 degrees, which kind of clashes a bit with some of the modeling that's been done, which reckons that it was probably had an initial latitude of 30 to 50 degrees. Like this figure here reckons that it would have ended too far south, its final location of Sputnik, if the Ridge Trough system was a paleoequator. But I will point out that the exact path that it's taken is sort of a little bit up in the air at the moment, and it might have changed course sort of as the basin was infilling with nitrogen ice. It may have sort of gradually changed course. So that's something that Pat and I would kind of like to address in future. And then finally, what does this mean for the rest of Pluto? One of the big sort of queries about Pluto is why we see so much more sort of thick thick deposits east of Sputnik and so few to the west. This is finally the cross section in all its glory. You can see to the west here, I've got sort of these generally quite bare terrains with just some of the thin mantles here, and you've got all the great thick deposits on the east here. So generally, yeah, there's a volatile abundance decrease as you go from east from Sputnik across the far side. So one of my colleagues at Ames, Tongi, has done some climate modeling, and I've worked with him a lot in sort of some of the geological studies I've done. He reckons that in the post-Sputnik era, after reorientation occurred, the existence of Sputnik Planitia is kind of like the main regulator on Pluto's climate, and he thinks it set up this westwards retro rotation of the atmosphere, so that basically, yeah, Pluto's atmosphere is sort of slowly rotating westwards around it. And he also reckons that the regional scale topography and albedo is important controls on volatile ice deposition. And I think that following the Sputnik impact, this eastern part to the east of Sputnik generally showed some more sort of topographic variability compared to the very flat western portion. And that this sort of was quite conducive to the deposition of methane ice here. So following the Sputnik impact, this may have all looked quite kind of the same, the Hayabusan, the Tartaran, and the Veneran parts, but gradually more and more methane started to accumulate to the east of Sputnik and gradually built up, and so starving the west of Sputnik of any volatiles, which is why it sort of retains its very cratered appearance today. And so it's why we have generally quite much younger landscapes to the east of Sputnik, but also we have the sort of the climate zone effect happening as well, the latitude impact. And while more and more methane was accumulating to the east, we got especially high methane accumulation in the diurnal zone, which forms the very thick bladed terrain deposits down here, which superposes the Hayabusan deposits here, and which is we can see is much younger than the Hayabusan stuff. So that in a way is sort of maybe my grand theory of everything for Pluto that sort of stems from the mapping I've done to try and explain sort of why we get these very sort of differently aged landscapes across its surface, with the Rhaetian group down at the bottom kind of being a wild card, and maybe due to endogenic activity, recent endogenic activity, perhaps forming cryovolcanism down here. So, okay, I've probably gone over a little, so I'm just going to leave this blurb of summary there, but I do want to leave, yeah, a few minutes for questions. So thank you, and I'll be happy to take any.
All right, thanks, Ollie. If we have any questions for Dr. Oliver White, please leave them in the chat, or you can raise your hand using the mechanisms. Also, the reactions, you can express applause, and you can express your appreciation for the talk in the chat also, if you like.
Or express skepticism.
All right, we're getting some applause here. Maybe 5 or 6 or 7. Okay. Yay. All right, it's building up. A crescendo. All right, since I work pretty closely with Ollie, I really don't feel like asking the first question here. Okay, a question has come across. Okay, excellent. I can read this question from John Littleton. The cartoon showing the cross-section of Sputnik Planitia suggested convection cells. Are there measurements / estimates of the temperature differential between the base and the surface of the convection cell, and what is the mechanism, energy source causing cell convection?
Yeah, thanks, John. So yes, that those numbers are there. I can't remember what they are at the moment, but they will be all included in Bill McKinnon's 2016 study on convection, where he lays out his rationale for that. So yes, I'm not sure at the moment what it is, so I can't offer an convincing, I can't offer a definite answer to that. But as for the mechanism, we reckon that the mechanism is probably just the heat of a few milliwatts that are trickling out of Pluto's interior, likely from whatever radiogenic decay is still happening in there. And I guess one of the main revelations of sort of New Horizons mission is showing that in the outer solar system, where you have all these volatile ices are stable in large quantities on its surface, you can get more bang for your buck with rather less energy. It seems just a few milliwatts trickling out can cause these enormous large-scale sort of resurfacing on Pluto's surface with this, if you concentrate all this very volatile nitrogen ice there. So that's the prevailing idea. I think there was another paper that came out recently that sort of argues for a possible interior to Sputnik means for sort of generating the energy required to produce convection. I can't quite remember the specifics of that mechanism, though. I think it was a paper by Vieira et al. But yeah, generally the heat trickling out endogenic is the idea for convection. There isn't really any tidal energy between Pluto and its moon Charon at the moment. So yep, probably just endogenic.
Let's see, I don't have another question on my board. I might just throw out a generic one about the interesting dichotomy between there being one Mongo impact basin and almost nothing in the middle between that one bin that's chock full of basins. And is that telling us about resurfacing on Pluto? Is it telling us something weird about the impactor distribution out there? What's going on?
So basically the question is sort of why we see this one enormous one and sort of very little sort of a similar size elsewhere.
Yeah, and you know, just nothing intermediate. There's a few.
Yes,
it strikes me almost like Venus in a way. It's interesting because you just have this. You have that one figure where just have a bunch of dots there, and they're all in a small size distribution. And there's of course there's no Sputnik Phoenicia basin on Venus, but that was a big clue as to what was going on Venus. So this seems like it's a big clue as what's going on Pluto.
Yeah, so I know Kelsey has done a recent paper on sort of linking crater sizes on Pluto to Kuiper belt object size distributions that probably has a lot of the answers you're looking for. I think from 2019 is when she published that. But yes, I mean, yeah, I'm maybe not quite sure how to answer that. I mean, other than I agree that it's kind of weird. And
let me throw out that one other thing there that, as you pointed out to me, that some of the Hubble Space Telescope results suggest that there might be another basin just beyond the visible range.
Yes. So, I mean, yeah, of course, one thing to remember is that Pluto has a habit of surprising us, and we, of course, haven't seen much of the southern hemisphere. But yeah, one thing Hubble did notice that that is in Hubble coverage that is not in New Horizons coverage at all. It was all completely shadowed. That portion is that sort of dropping off the south of New Horizons coverage. There's a particularly bright region that Hubble captured that some of us wonder might be sort of another sort of collection of another concentration of volatile ices, I guess specifically nitrogen ice, and whether that might be filling a similar sized Sputnik basin there, which would of course throw off a lot of stuff like true polar wander calculation. So there may well be another sort of comparable basin in its southern hemisphere that we haven't really seen much of at all. But I mean, maybe there is sort of, I guess there probably be, I mean, not really sort of being all that schooled in sort of planetary dynamics and sort of like formation from the nebula. I mean, it may be sort of lessons to teach us with respect to sort of this distribution of sort of objects that condense in their own little nebulas in the Kuiper belt, and whether you may have sort of a whole host of large features that crash into each other. I mean, Arakoth is interesting in that It's sort of being a contact binary that quite a few small KBOs seem to be, maybe sort of in the capability to get sort of nebulas with a large objects that crash into each other, but then that removes the large stuff, and then you're only left with smaller stuff to produce much smaller impact. So yes, a bit hand wavy on my part, but
well, I guess we do have some constraints on the on that Kuiper belt, or at least outer solar system impactors from the flybys of Uranus and Neptune.
Yes,
The moons, there's recorded records there. They're more quote unquote complete than than Pluto's record.
yes. Although yeah, there's nothing like an impact basin of a sort of Sputnik scale, I think, on those, or Triton. But again, we haven't. Maybe there's something. Yeah, and yeah. But yeah, maybe there's something hiding when we go back there.
Good time to send another mission, right?
Yes.
All right. The hour has just struck again. I didn't see any other questions on my board here. So let's all thank Oliver again, and congratulate him on a great talk. And it'll be recorded so you can see it. And join us again for the next LPI virtual seminar.
Yeah, thank you very much again for inviting me.
You're welcome. Let's see. I guess this is where the recording stops.
I guess so.
Something will happen.
Yes, thank you, everybody.
Thanks, Delia.